All right, everyone. I guess we can start our second. Let's have Anupam.
Okay. Welcome back, caffeinated. Just a quick reminder, we talked about comparative analysis. We gave the definition. We saw these two examples, rent or buy, ski rental, and this cat and mouse uniform search, search on a uniform metric. And we saw algorithms which were pretty much optimal. So for this one, we saw deterministic algorithms that were 2 minus 1 over b, randomized algorithms that were e over e minus 1 in the limit as b tends to infinity. For cat and mouse, we saw deterministic algorithms that were n comparative. We didn't see lower bounds, but maybe I can talk about it some other time. And we saw randomized algorithms that were log n comparative. And you might be wondering, cat and mouse is a very cute game, but where does this fit in, right? What's the big picture? What are we supposed to take away from that? Well, firstly, the idea of doing this search, you're searching for this magical location where the cat might not be visiting or where it's visiting last. And you're marking so that you make only log n hops before you reach that magical location is a very powerful idea. And it's an idea that you should keep in mind, as a search primitive. So let me, at least mention where all this leads. So here's one way of writing the cat and mouse game. So here's what's going to happen at time t. I'll see a cost vector, ct, and this belongs to, let's say, the positive reals of n dimensions. And what I have to do is I have to play a vector xt, which belongs to the probability simplex. So this is just saying that x is defining a probability distribution over their locations. And let's say that maybe I'm also going to say that xt is going to be in 0, 1 to the. It's it's just a 1 in one location and 0 everywhere. It's where the mouse is sitting. So think of the following thing, that the cat ct at I is going to be infinity if the cat is there, and 0 if the cat is not there. What do I want to do? I want to minimize summation txt plus sum over time of xt minus x. Is what I want to do. This is just the cat and mouse game. I can't be at the location where the cat is infinite cost. And I want to minimize my total. And this looks kind of similar, right? This is kind of what Shipra, Haipeng were talking about. In the regret kind of bounds, we are interested in this, actually almost this. Let me just relate this to, in regret, what we do is we do the following: ct xt minus 1. The algorithm plays first, and then the adversary plays next. It's this, I'm getting a look ahead. I'm seeing the cost vector before I make my action. There's a slight difference out there. There's no term, there's no movement term out here in the regret bounds. But we are comparing ourselves to the best fixed strategy, best fixed action in hindsight. So this was regret. This is what we are solving. And this is the problem that I talked about. This problem in general is called the okay, I'll just write down the term. Where should I write it down? I'll write it. Metrical task systems. Horrible name, but it's on the uniform metric. Just the uniform metric is captured by the fact that movement distances are unit between distinct locations. So the metrical task systems problem is a very general problem, and you can generalize this to, instead of saying it's the L1 distance, you can think of this as the earth mover distance or the Wasserstein distance according to some general metric between xt and xt minus 1. And then this becomes the general metrical task systems problem. It's a very powerful abstraction. And the ideas that we gave, suitably generalized, will give algorithms for metrical task systems as well. You might ask, why do I care about metrical task systems? Metrical task systems, a lot of problems you can formulate as metrical task systems. So for instance, you can imagine the following thing. You can think of caching. You have n pages in main memory, slow memory. You have k pages. You have a fast cache of size k, and n is much bigger. Requests come in, and when a request comes in, so a request is for a page. If this page is in the cache, you don't pay anything. But if this page is not in the cache, and the cache is full, you might have to evict some page from the cache, and then bring this page in. You want to minimize the number of evictions. This is the caching problem. Now, what you can do is you can imagine that why is this a metrical task system? This is got nothing to do with metric spaces and things like this, right? So here is one way in which this is a metrical task system. There are states. Every state of my algorithm is the contents of my cache. Right? How many states are there? And choose k. So this is state 1, this is state 2. There are n choose k, many possible states. And now my algorithm just says, I'm sitting at one of these states. In response to my request, okay. So now what's going to happen is, if I get a request for page 5, and page 5 is not in my cache, this will give me an infinite cost out here. It'll give an infinite cost on all states which don't have page 5 in their cache. So I have to move to a state which has page 5 in its cache. And the cost for that is really the difference between number of pages, maybe C1 minus C2 or something. The number of pages I would have to change to go from C1 to C2. So I can define a metric. It's this large state space, but it's a metrical task system. And so if you have an algorithm for metrical task systems, boom, immediately you have an algorithm for caching. You have an algorithm for a very vast variety. My V's and W's always mess me up. Growing up in India. So yeah.
Back to how you formulated the problem, there's I would have to have.
Wow. So this is the measure of my cost, and I'll always compare to the optimal cost.
Right. So imagine I fix the horizon of time. Problem be different if I'm not trying to maximize competitive ratio, but just minimize cost.
So I'm always trying to, in this case, minimize the competitive ratio. So I'm always trying to say arguments of this form, that my algorithm should have cost CT plus xt minus 1 is at most, let's say, alpha times CT plus yt minus 1 for all possible solutions y. And I'm trying to minimize this alpha.
Right. But so the adversary can pick those instances that are also where opt is very low to push that ratio up.
Absolutely. So when opt is low, I should be low. And when opt is high, I should be high. Absolutely. So far, so good. Oh, by the way, suppose caching, suppose let's just look at this special case, n equals k plus 1. So how many states are there? There are n states. Each contains k minus 1, n minus 1 of the things, right? N minus 1 of the pages. It does not contain one of the pages. Think of the mouse as sitting on that page. So there are n pages. The mouse is sitting on one page. A request for that page comes, the cat moves there. The mouse has to move somewhere else. That's like evicting that page. So this situation is exactly the cat and mouse game. If you want to get an algorithm for caching, you have to generalize the cat and mouse game. And that marking algorithm that I showed you can be generalized to caching in general. Yes.
I could see it like caching system, there wouldn't be necessarily like the behavior would not be adversary.
That's an excellent question. So, right, the competitive analysis was initially designed to be, its robustness is the first priority. So it's very adversarial in its thinking. But over the past 10, 15, 20 years, people have been trying to relax this adversarial nature. Can we get algorithms which are good on the average in some sense? Shuchi will talk about that. Ellen will also talk about aspects of that. So, and then there's this more interesting phenomenon recently where you can try to say, look, I want to be no worse than this worst case, but on good instances, I should be even better. That's a very, very commendable direction. I really like it. So, good. So the cat and mouse game is a special case of caching because of this example that I just gave you for this, this case. And it generalizes to MTS, which is a very general problem, which captures caching, another problem called K-server, and various other problems. What is K-server? I'm given a metric space. I have K repairmen who are standing around, K fire trucks. It's red, they're fire trucks, K fire trucks. I have a fire at some location, that's a request. I must move one of my fire trucks to that location. Which one of them should I move? I want to minimize the total cost. This is called K-server. This is a general metric. If it were the uniform metric, this would be the same as page. So all these are like various generalizations of this idea. And so hopefully I gave you some sense of how to solve this problem and how to at least take the first steps towards solving more general problems.
So you're always picking the vector from the same set. It's just the n-dimensional simplex.
Absolutely.
So it doesn't generalize the things like chasing convexes.
So maybe I'll come to that in a moment. So this X, this is, yeah, I could generalize this as well. So I could make this some other fixed set, maybe even Rn, for instance. In this case, maybe I just want to keep it this way. But so let me do one other thing before I move on from metrical task systems, is to give you a sense of what kind of results can be obtained and try to relate it back a little bit to regret minimization. So I was trying to make these connections as much as possible. Hopefully it will be interesting to you. So this is what I want. I want an algorithm such that for every input sequence, my hit cost plus my movement cost is no more than alpha times the hit cost plus movement cost of any other solution, including the optimal solution, but any other solution. So this I want for all y, which is the solution. You can prove such a result with alpha equals log n. So theorem. There exists a solution. There exists an algorithm that gives alpha equals order log n. But actually, there is an algorithm that does even better. So let me just tell you what it gives. It gives, and I'll just write it out here, 1 plus epsilon times the hit cost plus log n over epsilon times the movement cost. It just says, your solution is at most this much times any other solution. a nice sort of guarantee. And the people who are sort of experts in experts, their pulse is a little faster because these terms sound kind of familiar. And indeed, there's a connection out here. So let me make that connection. So this guarantee makes sense, right? Okay. So let me make a connection. So I want to say, suppose I have an algorithm that achieves this kind of behavior. Then I can get a regret minimization algorithm in the full information setting in experts. Let's do that. So let me just do the same setting as before. The costs, I have a sequence of costs. The costs are bounded between 0 and 1. And I want to look at my cost, which is CT times XT minus 1. This is what the regret minimization will do. I have to play first, and then I see the costs. This is just, linearity, right? CTXT plus CTXT minus 1 minus. What is this? Let's just look at one of these guys. It's at most the infinity norm of CT times the L1 norm of. What do we know about the infinity norm of the cost vectors when we are playing experts? We usually bound them between 0 and 1. What have we done? We've got CTXT plus the movement cost. Is an upper bound on my cost in regret. This is less than 1 plus epsilon times CT YT for any other solution Y plus log n over epsilon times the summation of YT from this guarantee. Epsilon at most half, 1, something like that. Yeah. Can it depend on n? I think it should be fine. Exactly, and you can get like square root type terms as usual. You'll see in a moment, actually. Okay. But in regret, what do we compare to? We compare to a solution which doesn't move, right? Let's say it moves only k times. Then, by the way, using the same trick that we did before, I'll say this is at most 1 plus epsilon times CT YT minus 1 plus YT minus 1. Same trick as before. This trick. Plus log n over epsilon times summation YT minus 1. I mean, this is smaller order term compared to this, so I'm going to just kind of just ignore this guy. What is this? If I'm looking at a solution that changes only k times, then this can be at most k. This gives a regret analysis. It says my cost one plus epsilon times the cost of any other solution plus k log n over epsilon, where we're moving k times. This is the shifting regret analysis, let's say from Zinkevich or any of the others. And yeah. So statements like this can also give you regret bounds. So, an analysis like this for the metrical task system gives you a regret guarantee. It's is number of switches in the in this benchmark solution.
It's like a switching rate.
Exactly, it's a switching regret. Absolutely. Good. So there are these connections, but also the techniques are connected. And then maybe the remaining time I have, let me give you an idea of the techniques so that you'll see how we prove things for online algorithms and why the ideas are connected. But maybe, I'll say one little thing. In metrical task systems, I wanted solutions where I didn't move too often, right? I'm minimizing my total movement cost. But we know this, that for regret minimization, stability is a very important thing. We want solutions which don't move too often. So at heart, the two are very similar. The techniques are also similar for the same reason. But they differ in the details. And what works in one doesn't work in the other. Hyping stock, I was thinking, which regularizers can I use? Most of the time, I just use entropy as a regularizer. Okay, I'm getting ahead of myself. Let me shut up and tell you a little more. Okay, questions about this while I'm erasing the post.
That was loss stability.
What's that?
That was loss stability.
That was, so I was being kind of vague in the use of stability out there. I wasn't, being technical in which definition of stability was. Yes.
So in your, so what happened to the other term? That was like xt minus 1 minus xt.
Oh, this guy?
Yeah.
So look at this plus this. That's the left-hand side out here. Right. Is at most the right-hand side, which is what I wrote down next. And then I, ignored this term because it's, I can really fold this into this and then.
You're looking at zero switch regret, then you don't care about the one over epsilon, is that right?
So zero switch regret. So you have to be at the boundary, you have to be careful.
Okay.
Because what's happening is I'm really talking about the number of times the Y solution changes.
Yeah.
And the Y solution always starts off at, me and opt have to always start off at the same solution. So let's say we all start off at uniform. So then this will be the distance between, this term will be the distance between the uniform distribution and the fixed Y that we're choosing.
Okay, so you still end up with root something.
Exactly. You won't get anything better than the experts guarantee, which is the best you can hope for.
But it's the penalty term, I guess. That was the penalty term.
That's the penalty. Shruti.
For bounded costs versus unbounded costs, there's also a big difference between
Absolutely.
competitive analysis.
Absolutely. Yeah, and thank you for emphasizing that, because in regret, you are making your action before the other guy. So if the other guy says that was infinite cost, you're like, oh, so there's not much to do, right? So you have to restrict yourself, and that comes out very cleanly. It pops out here that it's the cost you pay for this look ahead. I mean, these are giving you subtly better guarantees, but in the worst case, they all coincide. Good. Okay. Maybe I'll leave this for the moment, and then good. Other questions? Because what I'll do otherwise is I'll tell you about a couple of other problems. Right. It's not a usual approximation.
It's like a bind criteria.
Right. So this, if you are interested in this thing, there's a variant of MTS called unfair MTS. And this gives you this kind of guarantee. Right. So it is by criteria, and the way you do this is you play with the cost. You can scale up one of these costs so that they become of the same order, and then you look at the two aspects out here separately.
But they still look very different from what we would do.
Okay. So So the shortest way I would say this is, here is one way of getting this kind of guarantee. This kind of guarantee you can get using a mirror descent based algorithm. And it's just, the trick is going to be in the multipliers in front of the linear term and the regular variable term. By playing around with those, you can get these kind of guarantees.
We could start with these.
The techniques are very similar, absolutely. Any, yeah.
I get confused. And what is the objective here in MTS?
So in the MTS, I want to minimize this.
So why we get the lower bound? What I mean by that, but why you consider the inner product of secant the previous time?
Because, so what I wanted to say was, once I have this guarantee, I can get a regret guarantee as well. And this is what this regret guarantee is. You know, this proof is showing you this regret guarantee. So this, I'll say, is regret.
In this one, we get to see
And this is
so in online learning, we don't see the first.
comparative ratio. So in the sort of remaining time I have, let me tell you about a couple of techniques to analyze algorithms, and this will give me an excuse to tell you about a fairly general class of problems that we can solve online. So here's the class of problems we can solve online. Just, you know, it's a so imagine the following LP linear program. You all have seen linear programs, right? So so what I want to do is I want to I'm trying to minimize summation ci xi subject to constraints of the following form: a11 x1 is at least b1 and am1 x1 plus am, and let's say all the xi's are non-negative. This is just a linear program. It's a covering linear program. If you make all these entries, A's and B's, C is positive. So I'm going to look at the situation where all the A's, Aij, Bi, and Ci are non. And I'm going to not have time to write all this. So I'm just going to say minimize C transpose X. Ax is at least B, X is non-negative. Now consider the following situation where the constraints of this system are coming one by one. And every time a constraint comes, you have to find a solution that satisfies this. The online aspect of it just says you have to increase your variables. You cannot decrease them. Because otherwise you would say, oh, new constraint came, I'm going to just use Gurobi or my favorite linear programming solver to solve it. No, but you can only increase variables. If you bought something, you can't return it to the shop. What kind of results can you get? And the claim is that for all problems of this form, I can, so basically this I'll call monotone LP. Maybe I'll make it, I'll say covering LP. Solving. Covering is just this property can be done with. See, remember, this is my cost. I want to relate this cost to the optimal cost. Let's say the comparative ratio is at most order log of the number of customers. So I can give you a bunch of constraints one by one, and you can only increase variables. And still at the end, you'll say, hey, here is a solution whose cost is no more than log m times the optimal cost. Let me give you an example. Let's do it. Suppose I said x1 plus x2. This is my first, oh, so I want to minimize summation xi. I tell you the constraint, you say, okay, all the variables are equally important. I say x1 plus x2 plus xm, and n is equal to m, let's say. There'll be as many constraints as variables. x1 plus xm is at least 1. What should we do? You don't know anything about the future. So you better increase all your variables equally. Because here's what's going to happen next. I'm going to drop one of these variables. Let's say it's 1, but and I'll say x2 plus x3 plus xn. And then x3 plus xn. I'm going to give you constraints like this and xn. Of course, here in this example, I've dropped the first variable, the second variable, the third variable, and so on and so forth. But really, think of this as dropping a random variable from this to get the next constraint, a random variable from this to get the next constraint, and so on and so forth.
It's like the cat and mouse game where the variable is.
It's like the cat and mouse game. But I'm allowing you fractional solutions as well. So it's like the fractional solution of the cat and mouse game. Well, you could think of it as the probability distribution of where the mouse should be. That's 2 steps ahead of me. But just think about this right now. What should you do? You know nothing about the future. You should probably spread your mass equally. You should spread all the mass 1 over m on everybody. And then this mass, this 1 over m mass that you put on this guy is never going to be used again. It's a lost mass. Next time you'll increase all the variables equally pretty much. Everything's been symmetric. You'll put 1 over m minus 1 on all the variables, but this variable will never be used again. How much are you losing? 1 over m minus 1, 1 over m minus 2, and so on and so forth. This is harmonic number of m, log m. What's the optimal solution? Set this guy to 1. You have a solution of cost log m, optimal solution of 1, log m. This shows that essentially there is a log m gap. In this instance, there's nothing else you can do. You can make that formal if you absolutely insist.
Acting version maximization. Is it?
Yes. So there is one, and so you can talk about exactly the dual problem of system,
Right.
which is the maximization, the packing version, and that we can solve. But there we have to violate the capacities a little bit. So in general, that becomes difficult to solve because it's Shuchi's sort of talk. We'll talk about packing problems, and packing problems are difficult because if you come to the limit, and I give you a very lucrative item, how are you going to add that in? So usually we violate the capacity. But for now, let's do covering.
In the more general version of the problem, you said the competitive ratio is log m. So there's no dependence on n in the competitive ratio. Is that right? The number of variables?
Yeah. So this is a fractional solution where it does not depend on the number of variables.
Oh, wow. So even 10 million variables is still.
Yes. And in fact, there are algorithms where the number of variables are actually exponentially many, but the number of constraints are small, so you can actually do good things. Of course, running time wise, that's a problem, but then let's not go there for the moment. But this made sense, right? That look, the constraints came up 1 by 1. I maintained a solution that was always rising. And still my final solution wasn't that bad, was only log m bad compared to the optimal solution. And this you can do for any covering LP of this. This is covering LP, all covering LPs of this form, you can do it. Let me show you what the algorithm is. And for the special case where all the numbers are 1. A's, B's, C's. Oh, maybe not all of them are 1. They're either 0 or 1. So I'll give you an algorithm for the special case. So special case. Fractional set cover. And the thing looks like minimize summation. In fact, imagine all the columns are sets. So what is set cover? Set cover, there's a universe and there's a bunch of sets. S1, this is S2, this is S3, and there are elements which belong to some of these sets. I want to pick sets to cover the elements. So I want to say minimize the number of sets I pick fractionally, such that look at the first element out here. Let's say E1. So I'll give you an element, and I'll say all the sets such that E1 belongs to that set. Amongst all those sets, pick one fractionally. And then I'll give you element E2. And so on and so forth. This is really an LP of this form. This is exactly the kind of LP I was using out here. I just give you a bunch of, I give you say x1 plus x3 plus x7 is at least 1, and then I'll say x2 plus x9 is at least 1, and constraints like this. The only specialization I've made is all the entries are 0, 1. Is the problem clear? How should I solve this? So here's an idea. The idea is multiplicative weights. So here's what we'll do. So let me tell you the algorithm. So the algorithm is going to be, look at any variable xs. If it belongs, suppose this constraint just came in. I want to raise some of these variables, right? This constraint just came in. These two variables had some values. I want to raise them. Suppose x2 has a lot of value already. It should kind of tell me that like x2 was important somehow in the past. I should raise it more aggressively. So I'm going to raise x2. So when element E arrives, double x4. Okay. If summation of S such that E belongs to S, xs is at least 1, we are happy. We wanted to satisfy this constraint. Lo and behold, it's satisfied. Suppose not. Yes. Double xs for all S that contain. Take all the elements that contain the sets that contain element E and double them. The rich get richer. Sets which had a large value have even larger value.
What happens if this either overshoots one or doesn't quite reach one?
Good. So if this, the arrow is supposed to mean, you go back through this loop again. So if it doesn't, initially all the values were, let's say, very small. You double them, it's still like, very small. Go back again, double them again until, they were just below 1. They overshoot, they go to at least 2, at most 2. Not a big deal. That's it. We're losing logs out here. When we get more sophisticated, there is a problem though.
If there is some excess which can potentially cover, which is 0,
right?
But can potentially cover.
So the question is, what do I start off with? That's exactly it, right? So let's do the following thing. There are many ways of handling this, but let me just use the one which is the easiest. Xs is 1 over 2m, let's say 1 over m for all sets S. So I'm paying a fractional cost of 1. There are m sets, by the way. M is the number of sets.
So just Anupam, I think your notation, you should have log n in your monotone covering output. Like n is your number of variables. But now you have m as the number of variables in the set.
Oh, okay. Okay.
No, I think your competitive rate should be log n, right, and not log m in the blue text. Like when you do the randomized run, you would do some log the number of constraints, but isn't it number of variables?
Okay, so Ulla is absolutely right. That's the reason why I was making the mistake.
I think so.
Yeah, I think so. Sorry about changing something on a previous board. That's not a kosher move, but there's nothing I can do right now. Then I'll have to take it back, whatever we were saying. The exponential number of constraints is okay. Exponential number of variables not okay. Okay. Thank you. So let me go back to this. Is that?
No, you should probably use n. It's confusing.
Okay, good. Number of sets is n. Okay, but let's go back to, don't worry about the parameters, hopefully. I'm not confusing you too much. When an element arrives, initially, I give like 1 over n to every set. In total, I've paid 1. Right? 1 is, maybe it's an additive loss of 1. We can get rid of this. This is not important. And then whenever an element arrives, I double. And I double again, and I double again until the constraint is satisfied. And then I go on. So that's my algorithm. And how do I analyze? Oh, so my claim is, my theorem that I want to say is that this algorithm is order log n. I need to analyze this.
You don't break ties between the S's when you double?
So I double all the S's that contain this element.
So intuitively, there's one S that is very large, that contains everything.
Yes, so it could be the case that there's one S which is already at 1 minus epsilon, and all the other S's are sitting at this. So in that case, that S will become 2, almost 2. That's fine. This constraint is satisfied.
I guess you could have just proportionally increased everything.
Exactly. So I'm just trying to make things simple. Maybe you should just proportionally increase, and really you should do multiplicative ways. That's whatever. Some continuous version of this. But let's just analyze this guy. So how do I analyze this guy? I know, 3 ways of doing this. Since I'm going so slow, I can only do one and hint at another. But let me do one. So here's the proof. So this is the time to recall LP duality just a little bit. So the linear program that we are writing is minimize summation of XS such that summation of XS S containing E is at least 1 for all elements E, which we have seen, seen so far, and XS is non-negative. And you remember it's dual, it's maximized summation YE, a variable for every element, such that YE is at most 1 and YEs are non-negative. This is a covering problem, there's a backing problem. Oh, E in S. Okay. So the analysis is going to be in 3 steps. The first step is every time I do this, okay. So here's what I'm going to do. Every time I do one round of this thing, along with doubling the XS, I'm going to set YE. I'm going to increment YE. Here, constraint correspond to elements. So when this constraint came, a new variable appeared in the dual. Its value was 0. When an element arrives, YE is set to 0. And now every time I doubled the primal variables, I increased the dual variable by 1. You think back to what were primals and duals. The dual is a way of charging the primal. It gives a lower bound on the primal. I'm just constructing a lower bound. So the first thing I'm going to observe is that when an element arrived, how much did let's look at one round of this loop. How much did the primal change? Some variables got doubled, right? But the sum of those variables was less than 1. So the increment is less than 1. They were 0.99, they're 1.98, the difference is 0.9. The difference is exactly the sum. So every time I did this portion, the primal changed by at most 1. The dual changed by. At every point, the primal is at most the dual change. This happens at every time step. So the final primal, P final, which is my cost, is at most B final. Now, if the final dual were feasible, what do we know about the final dual? The dual is a lower bound on the optimal solution, right? This should be, by weak duality, this is at most the optimal primal. So I would have my final primal is at most the optimal primal. I have a better than optimal solution. This is amazing. So the point is going to be, so here, this is only true if the dual, bless you, if the dual is feasible. So the dual is not going to be feasible. But what I'll show, and this is going to be the final step, and for this, maybe I'll use this part of the board. Is that, well, actually, I could have just written there, but the final step, step 3, is that the YE divided by, let's say, log m, maybe constant times log m, are feasible. So I'm losing a log m factor. Log n, thank you. M's and n's keep colliding. I just need to show this. So let's just do that. What's the dual constraint? The dual constraint says all the elements in a set must pack to at least 1. So in order to show this, I need to show that all these things sum to at most log n. Look at this set S. Oh, for all S. Look at this set S. And look at the elements that belong to it. When did I raise their value? Every time I raise their value by 1, I doubled all these variables that included S. So every time I increased one of the Y's by 1, I raised XS by a factor of 2. Where did XS start off? 1 over n. What is the final value of XS? At most 1. Because if a set is set to more than 1, it will never be raised. It by itself will cover all its elements. XS started off at 1 over n. Every time it was doubled, the YE got increased. And XS can never be more than 1, because otherwise this if condition would be satisfied just by itself. Okay. Anyways, that's the
Here,
here we have the summation of YE in the set of S, so why don't we have the size of S in the right?
We could have, so we could optimize this thing further. I don't know if the size of S. So the reason why I don't, I'm not saying size of S, I'm just saying, look at any element in S that was, that caused XS to double. That's the element that is, every time YE for some E goes up by 1, XS doubles.
You would get like log the maximum number of sets and elements part of by doing what you said. You could, instead of initializing.
So what I could do is I could set this to be, instead of number of,
like instead of double X, like if someone is arriving, you could put the sets of those guys to be 1 over the number of sets covering that element.
sure. Instead of doing this doubling 1 by 1, I could.
No, instead of initialize by 1. Well, anyway, I just say that you could like refine what you are saying. I think is to get like log of the frequency, like
okay.
which is like the maximum number of sets they can cover an element, or like the support of the constraint.
So what Ulla is saying is that this log n, and what you're saying is that this log n, instead of being the number of sets, it could be log of the maximum number of sets that contain
Yes.
E, max over E. Kind of the frequency. Absolutely. The same kind of proof just used. But I'm not optimizing. The important thing was there were 2 ideas in this proof. The first, there was one idea in the algorithm, which is that multiplicative weights. If a set was important in the past, chances are it's going to be important in the future. Past performance is no predictor of future returns, but that's the best hope we have if we don't know anything about the future. That's the idea out here. So you double. And the idea in the proof is that you use the dual as a charging mechanism to show that the cost is not too high. Okay. So maybe at this point, I'll mention 2 other things. What you can do is you can do a continuous version of this, so that instead of increasing instead of doubling S, you could maybe go back to here, and I'll increase. I'll say that XS prime, this is the derivative. So I'm going to increase XS at rate XS plus, 1 over N. That's the same 1 over N out there over the cost of S. Then I can handle costs as well. Actually, I can handle, yeah. So you can have a continuous increase like this. Okay. And once you see this kind of continuous increase, you might say, well, what's really happening? Is there a sort of a deeper connection with the kind of regret-based algorithms and the techniques there, or the continuous algorithms? And so in fact, what you can do is here's a different solution that you can do. So you can say, whenever a new element arrives, solve this problem. It's actually a kind of a different way of viewing it, that the new solution at time t is the old solution, whatever. So is like a KL divergence between the solution and the previous solution, that X is a T transpose X is a. So look at solutions which satisfy the new constraint and which minimize the distance in the KL divergence. This problem will give you a multiplicative weights update. This is perhaps a more general way of viewing these algorithms, that our solution space, these are covering problems, our solution space is continuously moving upwards. So if I'm sitting out here and a new constraint comes in, I want to move to a feasible point. Which feasible point should I move to? And what these algorithms are doing is that they're projecting this point onto the feasible region, but the projection is not in L2. It's using the KL divergence. So maybe, I won't get more into this, but if you're interested, I can point you to references and we can talk some more. So it's sort of kind of a vast area. So I was trying to cover as many techniques as possible. So hopefully you got a sense of that. Maybe I will mention, I'll take 2 more minutes of your time. So where do you go next, right? I mean, this whole area. So the way I view it is there are several directions which are very promising. One is there are many classical problems which are still open. I mentioned the K-server problem, the fire trucks moving around. We don't understand that problem, for instance, completely. There are some gaps between upper and lower bounds. And many such landmark problems are still there. But one direction that I'm particularly excited about and which Shuchi and Ellen will talk about is how can we go beyond the worst case? I would like to have algorithms that are so bad or so good, that have a guarantee in every case, the robustness guarantee that we have out here. But on good instances are better. If we have more information, we should do better. So the question is, can we get algorithms which are more nuanced, where I have maybe stochastic predictions about the future, where I'm given 20 instances and 21st is promised to be similar. So there's this huge kind of spectrum between the knob of, sort of pessimistic, the kind of robust bounds that we get, and the offline bounds that we can hope for. And so, that is something that perhaps this group of people is particularly suited to, because these are the kind of things that interest you as far as I see. So hopefully we can talk more about that. If you have questions, I'm happy to answer them. Cool.
Yeah, you said you had 3 proofs. You just gave one. You just mentioned the 2 others.
Okay.
Keep my name.
Actually, so one other proof is you can write down a potential function, and you can show that this kind of update rule, let's say, or that kind of, all these update rules are essentially the same. It decreases the potential. So you start out the potential as the optimal solution, and then you decrease your distance to the potential. So that's a potential function-based proof. And the third proof is via this kind of projection. So arguing that these kind of Bregman projections actually give you a good solution.
But this is the easiest.
This is the easiest.
We started with the simpler problem like this key rental, where we're able to enumerate, strategy actions, and we explicitly wrote the prime, like the basically the minimax formulation and solved for it. Can I think of this primal dual argument as some form of relaxation, because I cannot explicitly write down policies and instances, so this is some form of a projection of that, minimax formulation, or is it so? Is it fair to think about it this way?
It's very fair. It's often the way I do think about it, but I don't know if like a formal argument. But that is pretty much the way I think about it, that I can't write down the entire game matrix and stuff. So this is one way of projecting it down into a smaller space.
If I try to use these 3 projections, then how do I make sure that monotonicity of?
Good. So for these kind of covering problems, monotonicity comes for free. So if you just look at the KKT conditions for this, the monotonicity just pops out. For other problems where you actually, it's not a covering problem, things get hairy, and that's where the fun begins.
Instead of using the regularization, is there a perturbation version of this algorithm? Something that follow the perturb leader instead of regularize?
No, but there should be. And it really comes down to the unconstrained versus constrained optimization issue. So there's some technical details, but there should be. That's the we can talk about. We can figure it out.
So instead of fractional set cover, if it is set cover, then monotonicity will not be.
I can still have monotonicity, So what happens is in sort of integral set cover is that I can take the fractional solution and I can do randomized rounding on that. I lose a log factor above this thing for the randomized rounding, but I can maintain monotonicity. So, variables, the fractional is just in my head. And then I'm doing randomized rounding on that. Each time I'm rounding, I can get a different solution, but there are ways to de-randomize it as well. And then you can be actually, with probability 1, be getting the same solution, be monotone and all that.
For integral solutions, you're only adding sets.
You're only adding sets.
So this monotonicity constraint, like, what's the better way to think about it? Is it something that is our desideratum per se, or is it just like a tool to say, oh, look, we're making consistent progress?
So it is, at least in this setting, it's a desired property that if I bought a set, I cannot return it, because otherwise, if you were just given a new constraint, one thing you could do is you could just solve the LP again.
I could have like other constraints, right? Like that's
sure. So you can change the problem. This is just part of the problem specification. And removing it and adding other constraints would be perfectly reasonable. Okay.
It seems like really close, but I'm not sure what the monotone in the. And like I think the results also look really similar because the solution isn't going to be changing very much if you do monotone. So like the results almost like that too. So I'm just trying to figure out how to.
So I mean, maybe there is the naive representation of set cover MTS has this problem that the distances are not symmetric. Because I can go from this state to the other state, but I can add a set, but I can't remove a set. But if I remove a set, I don't get the money back. So at least naively, I don't see how to make it work. But there might be a different representation which allows us to.
One comment on that. It seems that you have one of your constraints with the convex body that changing. Right. So in the MTS, you didn't allow us to change the decision set. It was always a simplex. So
absolutely.
If you let it change, then it can capture this problem. Because every time that you get to see a new element, you have a linear constraint that is added. So there is an intersection with a new half space that you have to consider. Then changes the set that you are going to make.
So what you're talking about is a situation like MTS, where instead of me always outputting a point in the probability simplex, I output it in some polytope.
I didn't think that would matter.
Maybe that's a definite maybe. I don't know. Other questions? People ready for lunch?
Can we be careful here to get the Hartman?
Can we be careful here to get the? That's another maybe. I don't know. I haven't tried.
In that case, I think we can take time to thank Anupam again. The afternoon we will have 2 talks by 10 p.m.